Scientific notation is going to be a very useful way for us to express our measurements this year, especially when we start working with things that are either very large or very small in quantity. I like this website because it really puts into perspective why we would need to be using scientific notation at any given time. So let me wait until this loads. We'll take a quick look here. You can see here that this is representing the sense of scale for us as humans is about a meter. And if we zoom in here, we can see things that are smaller. And you can see as we get closer and closer to smaller objects, we start to get to more useful units of denomination, such as the millimeter, to express these very small things. You can see here I'm getting into the micrometer range, and we're talking about the sizes of viruses. And then we get even smaller to the size of an atom, and we're talking about quantities that are 10 to the negative ninth in order of magnitude relative to a normal meter. I can also use scientific notation to express very large things, thousands of meters, like the Eiffel Tower, or even things that are much larger, like the sizes of galaxies and solar systems, 10 to the ninth meters. So you can see here that it's more useful for us to use scientific notation in very specific instances. The components of any measurement in scientific notation are some number between 1 and 9.9 repeating, multiplied by some power of 10. And like we talked about earlier, these numbers that are not powers of 10 give us the number of significant figures for that particular measurement. Okay? So first step is to really identify, okay, well, where's the decimal in the number? The decimal is obviously after the last zero. And then depending on how many spaces I need to move that decimal to make a number between 1 and 9.9 repeating is what I'm going to do right now. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces is the number of spaces that I had to move it. So therefore, the number of people in the world expressed as scientific notation would be 7.94 times 10 to the ninth power. Okay, why is it the ninth power? It's because I had to move that decimal place 9 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9. The same thing holds true with very small numbers. So if I have the wavelength of a sample of light, right, 0.000000095, it's kind of annoying to keep writing those zeros, and that's why it's useful to use scientific notation in these types of circumstances. I'm going to take that decimal, 3, 4, 5, 6, 7 spaces is the number of spaces I need to move it to make not the number 9.5. So 9.5 times 10 to the negative 7th. The one thing to keep note of is that very tiny numbers give you negative exponents for scientific notation. Very large numbers are positive exponents. Okay? So that should be it for our quick introduction as to how we convert back and forth. Take a moment, see if you can do these 4 practice problems. The answers are below. I'll give you a moment to pause the video and do that, and then we'll regroup here as a class if you have extra questions. Now to go backwards from scientific notation into standard notation, we're basically undoing what we just did here. So 1 times 10 to the 7th, I know that that's going to be a really big number, right? Because it's a positive exponent. So that means I got to push my decimal place to the right. How many spaces am I going to push it? 1, 2, 3, 4, 5, 6, 7. Every place that I had an empty spot, I'm going to put a 0 as a placeholder. You can see here it comes out to be the number 10 million. Okay. Now, if we have a very small number, right? Negative exponents being tiny numbers. So I have 8.6, but instead of moving my decimal place to the right to add more zeros to make it a big number, I'm going to move it to the left. So you would say, oh, you're just going to add 7 zeros in front of it. Well, not necessarily. We've got to count the number of decimal places that we're moving, right? 1, 2, 3, 4, 5, 6, 7. but the number of zeros that I need to fill those spaces is only 6. So that's the tricky part with going back and forth between scientific notation if you're dealing with a really tiny number, okay? Here's a few practice problems for you to try on your own. Pause the video, go ahead and give them a try. We'll go over these as a class if you need some help. And the last thing we're going to go over is how we deal with multiplication and division with scientific notation. Now, there were instructions in the summer work on how to express your numbers using the E button on your calculator. We're going to go through a quick demo in class on how to do that. But for the time being, I want you to look at these two numbers, right? We have the length of a cell, and the length is being expressed in micrometers. The length is 5.00 times 10 to the negative second, and the width is 7 times 10 to the negative first. Well, to deal with the scientific notation measurement and calculations that go along with it, it's easiest to split your math operations into what's happening with the power of 10 and what's not the power of 10. So if I look at my measurement here, I'm multiplying 5.00 times 10 to the negative second, and multiplying that by 7.00 times 10 to the negative first. Now, the easiest way to do this, you can do this without a calculator. That's why I picked these numbers. They're nice round numbers, right? So 5 times 7 is 35. We'll keep it to 3 significant figures because each one of these has 3 sig figs. And then you can multiply the powers of 10 by using your rules from algebra, right? So any base number to an exponent, you multiply them, you add the exponent. So 10 to the negative second times 10 to the negative first is 10 to the negative third. But there's a problem. This number is not expressed as a proper number in scientific notation. So if we're taking a big number and we're making it smaller, right, by moving this decimal place over to the left, it makes our exponent increase by 1. Increasing by 1 on the number line would mean from negative 3 up to negative 2. So my final answer would be 3.50 times 10 to the negative second. And that's my final answer, but I can't forget that I have micrometers squared as my final unit. Okay? So that was a problem involving scientific notation. Let's try another one here. We have a density. We know how to find density. So why don't you try this one without a calculator? We'll go over it here in a minute or two. To find the density of an object, right, you take its mass divided by its volume. 2.00 times 10 to the 7th grams. We divide that by 8.00 times 10 to the 4th milliliters. Okay, so first things first, I'm going to take my two numbers that are not powers of 10, and I'm going to divide those two numbers. So 2 divided by 8 is 0.25, or 1/4. I'm going to add a 0 on the end of that because it has 3 sig figs, 3 sig figs, 3 sig figs. Now, to follow the correct order of operations when you divide numbers that share the same base, 10 to the 7th divided by 10 to the 4th, I subtract those exponents. So 7 minus 4 is 3, so times 10 to the 3rd. Now, I need to make this a bigger number, right? Because I need to make this a number between 1 and 9.9 repeating. But the number itself, 0.250, is a small number. So by changing it, I'm actually taking my exponent of 10 and making it smaller. So it's going to drop by 1. So my final answer is actually going to be 2.50 times 10 to the second. Here's a few more calculations with scientific notation. You can use your calculator. It might be a good time for you to practice using that E button. I'll go over how to use that in class if you're confused. And here are the answers. So pause the video, work through these, and make sure you can calculate using scientific notation.